Just to give everyone a little update as to where ASC is currently working with the A-SAPTM process, I'm going to build a little bit upon what Harris talked about. It does require a lithography change. One of the fundamental changes we make is using a thinner, more advanced. By more advanced, it just means kind of a more leading edge technology dry film. Typically, we're changing from our standard 50 micron dry film down in the neighborhood of 25 and 30 micron. That is really just a nod to try to be able to maintain some capability of putting a mill of copper in the hole. Because remember, on outer layers, we're generally trying to plate the circuitry and the holes at the same time. So your minimum plating thickness requirement in your hole is going to have a direct impact on what you're going to be building into those dry film valleys, we'll call them, to form your circuitry. So we need to be aware of that, because if we push much below the 25 micron range of line and spaces, we start to desire using thinner and thinner dry films. Now, I don't know what your experience was with Crane, Harris. I don't know what types of films they were working with to realize those 15 micron features. But we're hoping that that technology and those thicknesses of dry film will allow us to explore that. Current limitations in our imaging equipment, our LDI, basically put some pretty hard limits on us currently at about 25 microns. So currently, as Harris touched on, we're working with several different OEMs on biocompatible, if that means implantable circuitry. Biocompatibility in these cases is defined by using very noble metals that don't react when implanted or in contact with the body. Those require some special plating processes, nothing overly complicated. But we're continuing to work with Averatek very closely on those. We've developed multiple laminates that we would say are ready for production, such as FR4 Flex hydrocarbon, and as Harris indicated, the ceramic filled PTFE type products like the CLTE and the Rogers 3003. And we're developing the plated through hole on double-sided and multi-layer product. We're still overcoming some challenges in that respect, but nothing that we think will be too limiting. Peel strengths been very, very good. I can certainly echo the results that Harris demonstrated in his table. The peel strength on Flex is very good on hydrocarbon materials. The Rogers 4000 series, being an example of that, are extremely good. And again, on the ceramic filled PTFE's excellent peel strength capabilities. We've met our imaging goals. 25 micron lines and spaces don't seem to present any issue for either the imaging or the developing stages. Obviously, they don't present any issue for the plating process. We are looking at technologies to be able to push that further below 25 micron, and we'll keep people posted as that develops. One aspect we didn't think about initially when we considered the Averatek process is we need to make sure that we have a reliable way of inspecting these lines. And so we've actually upgraded our capabilities in that respect to make sure that we can push the boundaries below 25 micron if needed. Another interesting technology that we added was the automated optical shaping of copper. It allows us to do minor copper shaping of some of these fine features, making manufacturing very practical and realizable in our current manufacturing environment. Next slide, please. These are just some examples of, on the left, 1 mil line and spaces produced at ASC on that BGA array. And on the right-hand side, we just have a simple cross-section of 1 mil line, 1 mil space, 25 micron. Unfortunately, I wish the cross-section was a little better and the filling was, but as you can see, it generally achieves the near 1:1 or above 1:1 aspect ratio that Harris was talking about using a 30 micron film. Next slide, please. I also want to talk a little bit about we call it via filling, but in general, the IPC refers to it as protection of printed board via structures. More importantly for the circuit board designer is the aspect of being able to reclaim usable pad space or a place to locate your components. So we're going to cover how the IPC defines the various via protection structures and some of the methods that we use to implement them, as well as some of the issues that we encounter and some recommendations that we might have for designers in utilizing these types of structures. Next slide, please. Most common and probably the simplest variety is a tented via. And when we talk about a tented via, it's generally using a dry film product, meaning it's got a product that is truly capable of stretching and bridging across the opening of a hole. And these are type 1 tented vias, with the top form being a non-recommended method of tenting on one single side. Usually in these cases, these are applied before final finish is applied to the board. And so you would have exposed copper inside those open vias of the top example in this illustration. Problem with that is chemistry can get entrapped in there, both the chemistry from our processing and final finish, as well as the assembly preparation, cleaning, and post-cleaning operations. Generally not recommended, but the bottom example below using a dry film resist is readily doable. You obviously have a completely sealed cavity, so that excludes the entrance of any chemistry, whether for us during final finish or at the assembly operation. Next slide, please. Type 2, tented and covered vias. These would basically be tented with dry film and then covered with a subsequent solder mask application. Fairly similar aspects as related to the first slide. The example on the top illustration shows you a single-sided cover. That's great for solderability, to prevent solder from wicking into those holes or to prevent anything from being drawn down through those holes if it's a conformal coating. But again, you have the issue or the question of allowing trapped chemistry in the bottom of that via, particularly if it's small enough or high enough aspect ratio that it's not easy to readily move solution in and out of that hole to make sure that process chemistry is fully removed. Again, very similar example on the bottom where it's fully tented on both sides, first tented with the dry film and then covered with the subsequent solder mask. Obviously, the excellent benefits, increased strength of the hole covering, just a better way in general to protect those unfinished via structures. Next slide, please. Type 3, plugged, and this is where we get a lot of confusion. We like to clarify the difference between plugged and filled vias, and that may just be a distinction that we make here at ASC. But when we talk about plugged, we're generally always talking about a screen applied LPI solder mask plugging. Now, it may be done with a specific hole plugging ink that is essentially a solder mask that is designed to fill and plug holes, or it just could be the LPI applied and imaged, exposed into those areas so that it remains to the developing process. Again, the same caveat applies to the top example. Caution when using a single side plugging, but in the bottom, you can see that it's been applied to both sides. It's usually recommended that the hole be completely filled just to prevent any trapped volatiles in those areas, but it's not absolutely required. A lot of the benefits, what we don't do in either of the previous examples is reclaim any of that real estate. These can preclude solder and flux from being pulled or drawn down into those cavities, but Again, they don't offer the reclaimed real estate to give you the full soldering area of any type of a pad and a surface mount device. Next slide, please. Plugged and covered, same thing. This is the most common type of solder mask plugged holes that we do. We do it in a separate plugging operation designed to pump ink into the holes, whereas the LPI, typical solder mask application operation, is actually trying to do just the opposite. We're trying to make sure that we don't put excess ink into the holes because that can cause issues with trying to develop that dried ink out of those deep cavities. Remember, we're trying to expose and develop the 0.7 to 1 mils of solder mask thickness that we generally have on the rest of the board to define all your openings for your pads, vias, etc. In that case, we're trying to limit the amount of solder mask we have in there, and that would not be a sufficient volume to be able to plug most common via sizes. So in these particular applications, we will generally use a separate plugging ink. Be careful when specifying that, just so that people know that they have the availability to use that, because it can result in a much better finished product, much more reliable actual filling and plugging of the vias. Give them an option so that they can do it prior to solder mask, or at least in addition to it. Next slide. Filled vias. This can be applied by numerous different methods. We'll cover a little bit later in this, our particular method, but there's a wide variety. Most people are doing it with semi-automated or automated equipment nowadays, using actual pneumatic force or hydraulic force to pump the ink into the holes. Generally, what you've got is a finished plated hole. By finished, I don't mean final finished, which will be filled or pump fill this via filling material. It can be either non-conductive or conductive, meaning filled with conductive particles. And then they are typically, they can be uncovered, as in this example. And next slide, please. Or if we go to type 6, they will either be covered and then tented by dry film. In this particular instance, this would be dry film covered on the upper left and liquid film covered on the bottom right. Next slide, please. And then finally, there's the most common employed in these high density surface mount component devices is a type 7 filled and capped via. Most important aspect is that they are processed to metallize and subsequently plate the top of the via structure, reclaiming all of the surface mount pad area for solderability. It prevents the solder from being wicked down into these structures, as well as gives you a nice flat surface for solder paste printing and subsequent reflow. The benefits are obviously you can do via and pad and ball on via pad, as well as stacked via technology. Next slide, please. The actual operation of via filling, we'll cover a little bit of aspects of that. Next slide. So why do we do via fill? Obviously, I've touched on it several times. It allows via and pad technology. We can do micro vias in pads, through hole vias in pads. All of those can be filled to give you a flat planar surface. It obviously creates more space on the surface for components, allows the size of the PCB to be smaller because you don't have to dog bone out to get an interconnect to pass signal to another layer. And it gives you more design options for improved signal performance. Next slide. So here you see an example converted from the old traditional dog bone method. the image on the left showing how you have to route traces out of the pads. The example on the right, you simply place the vias in the pads. You reclaim a bunch of real estate on your circuit boards. I'm sure most of you have been designing like this for many, many years. Next slide, please. Some other examples. It allows reduced real estate usage on external layers, increased capture pad, solder mask clarity and registration, and you can eliminate pad cratering. Basically, the examples that we see here, you can see how we've reduced the number of actual pads designed on this board. The pads have now all changed to no longer being solder mask defined pads. They're basically changed to non-solder mask defined pads. Those all lead to better solder mask definition, which gives you better defined openings for your solder paste application and just results in better solder joint formation. Next slide. The types of filled vias that we're talking about are buried vias on substructures. Those could be filled either with the resin from the lamination process or with a separate via fill material. There's blind vias filled basically using a vacuum enclosure filling technology. There's through-hole filling techniques. Some of the areas that we need to be cautious on is maintaining a minimum hole size and paying attention to the aspect ratio so that we don't create issues when trying to fill through holes. The other aspect the designers often need to be aware of is the variety of hole sizes being filled at any given via filling operation. We need to try to balance those and keep them roughly the same size, because the dynamics of filling a 10 mil hole in an 062 board are quite different from filling a 20 or 30 mil hole in the same thickness board design. The example in the center top shows a stacked via with a copper plating filled microvia with a conventional filled microvia above it. We see a buried copper plating filled microvia in the lower center, and that pretty much covers that. Next slide, please. So what do we want out of a via fill material? We want them all to be 100% solids, but we need to pay attention to their ease of processing. We quite often see a reference to an old via fill material on most drawings. It's been accepted in general across the industry that you can use any of the most current standard materials, from the Tayo product to the San I product. We need to pay attention that the viscosity matches the job. So in other words, when we're trying to fill extremely small via structures, we tend to like a lower viscosity ink. When we're trying to fill obviously thicker or larger cavities, we like to use something with a little higher viscosity. At the same time, we need to be careful that the CTE of the fill material is matching as closely as possible the CTE of the PCB material as well. And in the case of some hybrid structures, when we're trying to select the material, that makes further challenges, because quite often they may have quite disparate CTE values between the different materials. For example, a multi-layer formed between a modern lead-free FR4 material and an older pure PTFE material might have vastly different CTE requirements. And so selecting a via fill material might become much more challenging in that particular respect. Lastly, what we look for in a via fill material is that we can readily plate to the top of it and that we have good plating adhesion. While IPC allows some amount of lifting of the cap plating to the top of the via fill material, most people generally frown on it. We don't want to cause any defects either when it comes to final assembly. So we try to choose materials that readily accept the plating without an excess of additional processing required. Next slide, please. In general, these are some of the pastes that we work with. We work with generally the two most common conductive products, which would be a Tatsuta AE3030 and a DuPont CB100. Both are copper with silver plating. Both give you decent conductivity, both thermally and electrically. We'll highlight the differences between those two materials in a subsequent slide. And then when we go to the non-conductive via film materials, as I said, we work with three of the most common types. Those are the most often we see on drawings. The one in the center, not often utilized nowadays. The one on the top and the one on the bottom, probably utilized 99% of the time. Next slide, please. Just to give you some contrasts, here are some of these common materials. They all have roughly the same properties. 100% solids, TGs in the 160 degrees C range. Sanding, they all have some resistance to that, which is kind of a bad and kind of a good thing at the same time. Harder or stronger materials tend to resist dish down, particularly when using brush style planarization. A lot of people are using that technology, and some people are moving towards a sanding style planarization, which can lead to slightly less dish down of those types of features. We look at how they behave through desmear, because the complexity of these boards typically means that they're multi-layer in nature. They're going to be going through some sort of a desmear process. They have to be able to withstand that type of chemistry, or you have to do a separate treatment, plating, and capping operation just for the filled vias, which can be problematic in and of itself, obviously adding cost to the overall build. All have good hole filling qualities and a reasonable pot life at room temperature. Next slide, please. Now looking at the conductive pastes. The DuPont material is kind of an old holdover. It's not available in a convenient packaging, so it becomes much more difficult to use. It also has a much larger particle filler size, so it's not very suitable to filling smaller holes. It's not necessarily 100% solid in nature. And the last thing I'm going to touch on, and probably the most important, is that it's considerably more expensive. So if you have older drawings that still contain references to DuPont CB100 and they're not specifically tied to a requirement for a certain CTE value or specific design requirement, it's often advantageous to open up the drawing to allow the options to use other different types of conductive via fill materials, because at the end of the day, cost is a major driver for every design. And when we look at the thermal conductivity, which is one of the reasons often cited for using conductive via fill materials, obviously the Tatsuta is superior in that particular respect at 7.8 watts per meter, comparing with 3.5. Next slide, please. So the Tatsuta, I think I've touched on most of these already. It's got excellent performance characteristics. If you didn't notice, it's got a TG that's 171 degrees C, considerably higher than its nearest competitor. It's 100% solids. It does a very good job of providing void-free hole filling. It's NASA outgassing listed, very small particle size for smaller holes, and it just makes it an easy product to work with. Next slide. Now, in general, we try, with all that said, honestly, we try to educate our customers as much as possible. And one of the things we want to make them aware of is, even though the thermal conductivity of a conductive via fill material is certainly higher than a non-conductive via fill material, there's still nothing when compared to the conductivity of the plated copper itself. The thermal conductivity of copper is 398 watts per meter. Thermal conductivity of silver filled epoxy is somewhere in the examples that we showed, somewhere between 3 and 7 something. So at the end of the day, 81% of the hole is filled with silver epoxy, but only 5% of the thermal conductivity or thermal transfer capability of the plated hole is supplied by the conductive via filling material itself. Increasing the copper plating thickness by 0.1 mil in the plated hole will have a greater thermal transfer capability than its conductive epoxy filled counterpart. So in general, if you want to improve the thermal conductivity, while these materials are an improvement, the newer conductive filling materials are an improvement over the older materials. Non-conductive via fill materials are much cheaper to utilize and much easier to work with in general, just because of the nature and the style of the fillers utilized in those types of products. Next slide. Via filling process, we fill using a vacuum enclosed BHF 300V. There's vertical varieties. I don't know that one method is extremely superior to the others. They're all very good, but we found that we get excellent results when using, or I should say, from moving from a semi-automated process to a fully automated process. Just allows control of aspects that you couldn't manage, such as traverse speed. It just allows you to fine tune your process to a much higher degree. It allows us to fill the vias in a single pass, which can allow keep you from creating additional void inclusion from having to fill complex designs in multiple passes. And obviously one pass filling minimizes the chance of voids. Next slide. Scavenging is an important aspect because when we're done with these, we want to minimize the need for planarization. So we actually have a device designed specifically to remove the excess via fill material from the surface of the copper. Essentially, it leaves the surface virtually clean, requiring minimum sanding or planarization to ensure that we have removed every bit of that via fill material, because if we don't, that's subsequently going to result in a short defect because we will not be able to etch away the copper in the subtractive fashion that most circuit boards are manufactured. Next slide. This is how we would planarize that surface using a Pola Massa orbital wet sander. There's multiple methods and machines out there to perform this operation. In general, this method works fairly simply, creates a very clean surface with minimal impact on the knees of fully filled holes. But as I'd mentioned, this style of machine does have brushes, so there is a bit of deflection on those particular surfaces. So you will get a small amount of dish down. You will not create a perfectly flat filled via, but again, IPC in most applications generally don't require that. Next slide. So when we're designing boards for via fill, generally we want to make sure that we keep to a minimum hole size of 10 mils. And when we say a minimum hole size of 10 mils, that means your finished diameter. That means after plating. That means we will probably drill it at a much larger hole size. When I say much, it might be a 14.5 to finish down towards your 10 mil diameter. So we'll handle that aspect of upsizing the drill. Hole size maximum, generally we like to stay below 30 thousandths of an inch. We've filled holes as large as, I think, 56 mils. It's not easy or straightforward or very cost effective, but it is possible. Lastly, we have to be aware of how thick these boards are. We pretty much stay to a maximum aspect ratio of 8:1, but we've obviously filled holes in boards, 10 mils in boards much thicker than 80 thousandths of an inch. Generally, the same rules apply for non-conductive via fill. Note that 1:1 indicates, I think everybody understands that note. So next slide, thank you. When the rules don't apply, holes obviously may be filled outside of recommended guidelines. The results in general is just understanding it can require multiple filling cycles. That can oftentimes add not only hours, but days to the actual production time of a design that you may need immediately. It can cause increased fallout if parts are rejected because of impartial via fill. It will increase the copper thickness variability, which can directly impact the etching quality of a particular design, because as the copper thickness varies on the surface due to multiple planarization operations, the etching is also going to vary along with that. And lastly, I think everybody understands what all of that means is an increased cost. Copper filled vias. Now, when we're talking about these particular types of designs, we're talking about copper plating filled vias. And the reason I draw that distinction is because we can mix the two technologies in our thought processes, but we need to think a little bit differently when we're talking about copper plating filled micro vias. In general, just some guidelines to go by. The current chemistry we utilize, and I don't know that this holds hard and fast across the entire industry, is generally we have limitations on minimum hole size of 3.9 mils. Quite frankly, that's as small as we can mechanically drill at this point in time. Maximum hole diameter is probably the most important thing to keep in mind, is that they're not designed to fill greater than a 10 mil hole. Maximum aspect ratio, that's height to width, is 1:1. And what they do for you is they allow for you to increase copper on the surface due to via plating. I should say do allow for increased copper on the surface due to via plating. While they do a great job of pushing additional copper inside the hole to not only fill and close it, they also do a good job of limiting the amount of copper that you put on the surface. But with that being said, if I'm filling a 10 mil deep hole, it's still going to require a significant amount of additional copper on the surface. This is an example of a copper filled blind via. This particular example was mechanically drilled. When we talk about forming these, we want to provide a minimal penetration into the capture pad so that we don't risk cutting through to the backside. The key aspects of forming these are adequate cleaning and preparation of the capture pad surface, and then obviously complete copper filling of the via. Lastly, we planarize to minimize the impact on surface copper so that we can realize some of these finer features that we talked about. Next slide, please. Forming of the via. I think we're getting a little short on time here. I'm going to start pushing through this a little bit. Generally, this just shows an example of a mechanically drilled micro via as the one that I showed in the prior example. Next slide, please. Just an expanded view of the interface between the filled via and the capture, I should say the target pad, with a conical drill. And what we're highlighting here is that we want the grain structure of the electrodeposited copper in the hole to match that of the clad copper of the target pad. Obviously, the net result of everything that we've learned is that the rough surface is not necessarily better. In the past, the old adage was if you want increased adhesion, you would increase surface area. In this particular instance, we have found that it does not hold true. Next slide, please.